So force measures a push or a pull of an object. So like you can figure out how much force is acting on two objects. Um, Energy is the ability to do work. Uh, so a lot of times energy is used for like calculating electrical energy. Voltage is very common in terms of like how much energy per something, like energy per charge or energy per kilogram. And then field strength, in terms of gravity, is its acceleration of gravity or electric field strength. So now these equations are in the IB formula packet. They are under fields at work, topic 10.2. They're written, these are all gravity. These are electricity or electromagnetism. And then they just, really the only one they want you to know for nuclear is equals mc squared. Um, and so they are there. I would say the ones to know the most would be, well, I guess all of them. But forces, if you can know forces, um, then you can probably derive the other ones pretty easily because you know energy is force times distance, and then voltage is energy over time. You can derive those. So what can we do with this? Well, let's say we had a helium atom. Here's a helium atom: two protons, two neutrons, two electrons. The two protons in the center are positioned at a distance of 1 femtometer apart. So that symbol is Fm. Uh, F is a prefix that means 10 to the minus 15 meters. Well, that's also on your IB formula packet. So let's recognize that. 1 femtometer is 10 to the minus 15 meters. The charges of each of these can be found in the IB formula packet. So each of these two things have the elementary charge. Calculate the force of repulsion between these two. So this positive charge right here and this positive charge right here are really, really close together. 10 to the minus 15 meters apart from the center of this one to the center of this one. And essentially, they're going to push each other off with a tremendous amount of force. Well, here's the formula packet where it says femto on the bottom, if it would. Yeah, femto, okay, present here. So, all right, here's some more useful information. So on the first part of the formula packet, elementary charge, that's the charge of each electron would be negative this, and each proton would be positive this. Masses of each of the objects in kilograms and atomic mass units, and another unit we'll talk about later. And then once again, I have those equations there we'll talk about. So let's think about this. How would we calculate the force? Well, we know that they're going to repel each other. So we're going to use the only force that involves repulsion, which is electrostatic force. Electrostatic force is equal to K times Q over R squared. I wrote it down here. Coulomb's constant K is in the form of packet. It's written down as, I usually just say 9 times 10 to the ninth, but it's written down as 8.99 times 10 to the ninth. Close enough. All right. Q and Q are both the elementary charges, which are both 1.6 times 10 to the minus 19 coulombs, and R is 1 femtometer or 1.0 times 10 to the minus 15 meter. When you plug those numbers in for K, Q, and R squared, you get a value of 230 newtons. That doesn't seem like much, but let's think about that. That's equivalent to 51.7 pounds of force for every single helium atom. Now imagine if you had a mole of helium atoms. Multiply this number by good old Avogadro's number. Holy moly, you get 3.1 times 10 to the 25th pounds of force for a mole of helium. That's how much nuclear repulsion force there is in helium. So it just goes to show you how strong some of these forces are. So obviously, the repulsion forces don't explode the atoms. That doesn't happen. They don't repel. Well, they do, but the atoms don't fly apart. So what holds it together? Well, the answer is the strong nuclear force. And when we come back, we'll talk about the strong nuclear force.